Hi, this is Charles Anderson again, running through some of the basics of Aspen Custom Modeler. This time what I've done in the fourth of this series is pulled together a somewhat detailed flow sheet. It's a completely fictitious flow sheet, it doesn't correspond to anything in reality, and there's a couple of fairly silly assumptions, but what I'm doing is trying to demonstrate how ACM can be used in a variety of ways rather than risk anybody's intellectual property. Okay, so what I've done is I've got a fictitious A goes to B goes to C reaction, A being my feedstock, B being a product of interest, C being a waste stream. And the A I've got coming in as a solid, molten onto an inert component D. So what I want to do is bring that A and D material together, slurry it up with some water, melt the A off the D, filter the remaining D solids away to go to waste, have the molten A then come to a reactor where A goes to B goes to C. I'm assuming C is a gas and so strips off easily, so I flash off the C. I then cool the whole material down so any unreacted A is a solid, so I can then filter the solid A away from my dissolved B, and my B is now my product. So that's the real simple stream. Let's just make sure it runs, which it does. What I've done is at the flowsheet level, I've put in some equations that allow me to look at the overall yield, so what fraction of the A material is leaving coated onto stuck on the B, reacted into C, or being thrown away here at the end as solid A, so I can see where my yield is going. I've also put in some economics so I can work out what the process is costing me to operate. So I'm spending this much on water, I'm spending this much on solids disposal, and so on. So that gives me a feel for how the economics are working. I've summarized all that information onto these two tabs, so tables rather. So this one, the economics table, is showing me the cost of doing various things. This table here is showing me the various key inputs, so my incoming solids, my rate of production, my overall yield, those sort of things. It also shows me where I'm getting my losses. So you can see right now the vast majority of my losses is coming as A leaving unreacted out of the back end here. So the first thing to do is to have a look at the reactor and see what can we do to tweak the reactor conditions. What I've done here is I've cheated and I've made the reactor, I've assumed it's a batch reactor. Rather than doing a dynamic simulation, what I've done is I've actually broken those simple reaction conditions down into an implicit Euler method, so I can solve the dynamic component of the reactor as a series of algebraic equations, and so embed it into a steady state model. What I've done then is I've broken my overall batch into 50 segments, each of which are 0.02 hours long or 1.2 minutes. And so I simulate an hour's worth of time, and then I choose what point on that curve to draw out my product. So if I have a look at the reaction profile, this is a profile plot that I can generate with one of these tools. You can see, as you would expect, A is being consumed, B is forming, and then gradually as the B concentration increases, so the rate of C formation, which consumes the B, takes off, and I reach a point where I actually have diminishing return in terms of the B. Right now, I'm operating at, I'm pulling the product at the 8th node point, so here. It's obviously well short of the optimum, so if I move up to somewhere closer to, say, here, so let's pull product at the 22nd node point. Have a look at the economics. I'm currently at 1.93, hit run. You can see that I save almost half my cost by improving that. My yield, my loss to B, which was almost 50%, has now come down to 12%. So that's definitely been a worthwhile thing to do. Although having moved this much further in, I've now started getting a significant amount of C being formed, and so my loss to component C has now risen from a small amount up to 20%. Okay, if I looked at my reaction parameters, you see my activation energy for the second reaction is less negative than the reaction for the first one. So that means if I can raise my reactor temperature, I will make less, I'll slow down, I'll speed all the reactions up, but I'll speed the A goes to B reaction up more quickly than the B goes to C. So let's pretend that the maximum I can bring this material to is 75C. So let's raise the temperature to 75C, rerun the simulation. You see I did move, the curves have moved quicker. I've moved towards the left. The peaks got slightly higher. I've now also got my maximum here at closer to 14. So let's move to use node 14 as my product point. So I've come from 80 something down to 77. If I move again, I move back up to the cost. So the cost's gone up. That's surprising. I would expect the cost to have gone down. Why is that? Well, if I look at where I'm spending my money, you can see that the spend on solids is pretty significant compared to all the other spends. And so by moving to a shorter time, I'm actually sending more A to waste. My loss to cake is back up over 10%. But that solid disposal is really expensive, so it behooves me to try and minimize that cost. So what can I do? Well, the next thing to try would be to recycle that material. So this is, at the moment I'm sending to waste a nice stream that's 50% A solids and water with a little bit of B, which is a useful product. So I may as well recycle that back to the front end of my process. So why don't I do that? Let's come into my library, find a new stream. Let's pick up that base stream. I'm going to pick it up from A, and I'm going to recycle it back into my reactor. And then just to make it look pretty, I'm going to move this points down, and you can see how it's going around. Okay, so now, excuse me. So by default, that splitter sets it up with 50% recycle. Let's make sure that that runs. It does. You see I've gone from 80 something back down to 70 something. Why am I recycling 50%? That's just the default value. I could increase that up as far as I like. I could presumably recycle all of the material. I'm going to be slightly pessimistic and assume that I'm going to risk having some unmodeled impurity build up. So I'll recycle 99% and see what that does. And there you go. That saved me another 10 plus cents a kilo, which is pretty attractive. If I come back and have a look at my process summary, you can see now I've got almost no loss going to A. I still got a pretty substantial loss going to B. So now that I've got a recycle though, rather than getting the maximum single pass yield, I could consider moving back up to reduce the amount of C being formed and just accept the fact that I'm going to spend more recycling that A material. So let's have a look and see what that does. I've got too many windows open. Okay, so what I'm going to do is I'm going to pull my product at a shorter time period. Let's pick, let's say 8. Let's see what that does. So I've gone from 59 down to 53. That was definitely the direction of goodness. I could obviously do an optimization to try and work out where the best point is, but you get the concept, I hope, through doing that. Okay, so if I have a look at where my losses are coming from, there's still quite a lot coming from C. So let's just see if we can reduce that a little bit further. Yep, so that's starting to look fairly attractive. My losses to cake have come up. I've got a much bigger recycle flowing around now, but my losses to C are reduced, so overall my economics are looking good. I'm also losing 4% of my material to the product D, and right now I've got this wastewater or wash water stream included, but I'm not actually using that wash water. So why don't I use that wash water to try and improve the amount of material there? So let's bring it up to a wash ratio of 0.5. Actually, let's try 1 and see what that does. So I'm going to use 1 kilo of water per kilo of wet cake just to see what that does. So 52.7, I hit run. You see that's 51.2, that's brought it down. And then let's try using slightly less water, because the more water I use, I have to buy that water, and I'm diluting out my reactor. So there may be an optimum somewhere shorter, and yes, it looks like I can save a little bit going to 0.5. So that's all looking quite good. The other thing that's happening is the water's cold, so I'm cooling down my reactor as well. So I'm forming a little bit more C as a result. Okay, so I've worked through various options there in terms of how to change the flow sheet. The big cost remains the solids disposal. So let's just then let's magically assume I can come up with a different way of disposing of those solids where I essentially just give it to somebody. So rather than sending it to landfill, I find somebody who's interested in having those D-solids, and I'm going to divert all of the solids to that new user to reduce the material going to landfill. You know, I don't even have to get any money for it. I'm just giving it away. Let's see what happens if I give away those D solids. And there you go. I halve the cost. My spend on solids disposal has gone from $100 or $200 down to just $10 for the little bit of A that I'm still disposing of as I fail to close my purge. And I've got significantly better economics as a result of doing all that. Okay, I think that's where I'll stop the demo for now. Hopefully you got a good flavor